You want to kick it off?
Sure. So if you're in the manufacturing industry, or if you've studied mass production at any level, you've probably heard of the cost production or the cost volume curve, which basically relates to the cost that exists to make parts in production compared to how many you're actually making. And so you may have the intuition already that as you create more parts, the cost per part gets driven downwards because the overhead is diluted across all of the volume that you're creating.
And on a macro scale, this goes all the way back to like the Industrial Revolution, where you see people making massive numbers of similar parts instead of bespoke parts, and that driving costs down and allowing people to grow their businesses, grow the number of the inventory, and grow the standardization a ton. So within this kind of sphere, we see, Nick, do you want to draw our like a lovely line on the back?
Sure.
Kind of talk about it. Is what you see is this kind of asymptotic start with 0, where something costs a ton to make 1 to 5 of. And then as you get out to the thousands, tens of thousands, even more, goes to a very cheap price. And so this is on the back of a couple things. This decline's really on the back of two things. The first one is an increase in efficiency. So obviously, as you make more, you get more efficient at making them. And the second one is a distribution of overhead costs throughout the volume of the part, which I was going to let Nick talk about.
Yeah. So. And when we talk about these different fabrication methods, a lot of them include injection molding on the plastic side. And then on the metal side, we're talking about different types of casting, sand casting, die casting, which we're going to talk more specifically about today. And so the curve I just drew behind us, I'm not sure how well you can see it, but basically, if you're making 0 units of something, or 1 unit of something, and you're die casting it, the major cost of that is the tooling. When you're die casting a part, depending on the complexity, the size, and the accuracy you're looking to get in that part, tooling is on the order of tens of thousands of dollars often. So this curve is approximate for if you were paying $25,000 for a die cast tool. And as you can see, so on the y-axis, it starts at $250, and so it comes from way off of the graph down. And as you get up into like the $5,000 to $10,000 range, that's when it starts getting down to $10 per part, which is closer to where you're looking to get. And so if we have a $25,000 tooling, we're looking at making 10,000 units of something to get that part down into like the $5 to $10 range, including all costs.
Yeah, and so here's where you see die casting is a perfect example of kind of the dichotomy in cost per unit parts. So obviously, when you're talking about making a part, it's always in cost per unit. But really, the cost per unit costs are broken down into two things. The first is the actual cost it takes to make 1 unit, ignoring the tooling, the fixtures, the anything like overhead related. So that's a material cost, that's labor to make 1 part, that's additional labor to make 1 cost. And what you usually see is for something like casting and injection molding or these mass production methods, that number is basically 0. It's not 0, obviously. There's material cost, but compared to the rest of the cost, you're really seeing a really low component there, and that's what allows them to scale so well into the many units. The other component of that is the other component of cost is the overhead cost, and the overhead cost is largely what's responsible for the curve downward. And as Nick says, when you're having an overhead cost that's large, to get to something where the overhead cost is distributed across enough parts in volume to make the overall cost per part low, you're going to take a larger volume. And when you think about this, pretty much every fabrication method that exists, whether it be casting or machining or forming, has a chart that looks something like this. Some, like machining, are a little bit shallower because machining's overhead cost is lower and per unit cost is higher. But most have some unit costs where the cost per unit on a low volume is high and on a higher volume is much lower.
Yeah, and so if we start looking at metal 3D printing, the overhead cost that you have there is essentially 0 because you're not having to make tooling to create parts. All you have to do is put your design into the printer, and then the printer is automating the rest of the process for you without the need for expensive tooling. So the curve, I guess you could say, but it's more like a straight line when it comes to 3D printing, is more just like a horizontal straight line. So, maybe it costs $30 to print a part. And whether you're making 1 part or 1,000 parts, each part is going to cost the same amount because all you're paying for is the small amount of labor that goes into it plus materials plus power, and that's essentially it. Yeah. And so as you can see on this graph, it's approximate, but if you're below this 5,000 units mark, the cost per part compared to die casting is that this isn't necessarily taking time into account, but the cost per part is going to be less because this is lower on the y-axis of this curve.
Yeah, and so with that, we want to kind of dive into the reasons why 3D printing is like this. So 3D printing is really unique because of this kind of like zero overhead. That's probably the most unique part about the process from a cost perspective. When you look at the other side, the reason that most of these other processes have that curve downward is because of tooling and fixtures, and because even in a process like casting or molding, where your actual fabrication process is largely additive, there's a subtractive element. In casting and molding, it's obviously machining a mold. It's something using forming, tooling, or stamping. You have to make the tools. So there's this large, the overhead cost goes to getting ready to make a part. In 3D printing, because it's a truly additive process start to finish, that cost doesn't exist. So there's obviously some cost associated with designing a part for manufacturing and laying it out on a print bed and doing that cost, but most of that operation is done by an automated slicer. So you're not really doing that work there. And when it comes to fabricating the part, you're not actually making the part. Like an automated tool path creates the part for you. So it's not like you're going to be able to optimize the creation of these parts in basically in large volumes. So the same thing that kind of lends itself to being causing 3D printing to be flat also kind of limits its efficacy in massive volume production. You're not going to get cheaper as you make more and more of them. But for that low to medium volume, or that basically less than N volume, where N is that equalizing point between where the cost per part of a 3D printed part and a machine part is equal, that's where 3D printing is cost viable.
Yeah, and so this becomes even more complicated the deeper you go into it, because we're assuming a fixed, a $25,000 tooling cost for this die cast, when in reality, tooling for casting is very variable depending on geometry, complexity of the part, size of the part, et cetera. And also, the cost for printing is mostly, dependent on the material. So larger parts are going to be more expensive to make. And so but the interesting thing is with 3D printing, metal 3D printing included, as the complexity of the part increases, that doesn't necessarily mean that the cost increases, because since you're not making tooling for a 3D printer, that complexity cost is completely taken out of the equation. Whereas when you're making tooling for a cast, those complex parts are going to take a lot longer to machine if you're machining the tooling, et cetera. And so what that does to this curve is it actually shifts the curve upward as you increase the complexity of your part. So let's say instead of a $25,000 tooling for this cast part, the tooling costs $100,000, which is something that happens in the industry. So the curve, what is going to happen is it's going to shift up and it's going to shift to the right. So your initial parts are going to cost a lot more, and you're going to have to make a lot more parts to actually reach that point. And so here we see when our tooling was $25,000 to begin with, we can get down to around $10 a part before we get to 10,000 units. Whereas if the tooling was $100,000, we're going to have to make 30,000 units to get down to that same price. And so then we see 3D printing is a viable option in terms of cost, all the way up to this like 8,000 unit mark.
Yeah, and I think that really points out this other thing that's really different between like a more conventional manufacturing process and 3D printing, which is the driver of the cost per unit. So when, as Nick says, when you're looking at most of these die casting, molding, machining, the thing that costs far more is complexity, because the operations required to make something that can make either a tool or to make the part itself that's complex are the expensive thing. When you're starting from a big block of metal, the hardest thing you can get to is nothing, or a very intricate shape. Whereas 3D printing is the opposite. 3D printing starts from nothing. So creating an intricate shape doesn't actually imply anything extra. In fact, what's actually least efficient in 3D printing is printing a big block of metal. So what you see is if you can run your part on the spectrum from block of metal to like very spindly part, anything that's closer on that spindly, more unique, geometrically complex, specialized curves, that stuff is the stuff that where 3D printing is going to get even further out into that production curve, as opposed to a more blocky, simple part where what you're going to see is that number will equalize more quickly. I think it's worth noting that either way, it's probably cheaper to create low volume parts with 3D printing just because of the expense associated with creating 1 to 5 or 1 to 20 parts of any number with any other fabrication system. But those two things really drive where you're going to see the advantages of printing.
Yeah, and in terms of complexity, we talk a lot about how machining a complex part or machining where you have to subtract away a lot of the material is very expensive. Another added expense to a complex part in a die casting scenario is when you cast a part that has overhangs or holes or other complex geometries, you have to add inserts, which is an additional piece and additional complexity you're adding to your mold, which makes your tooling even more expensive. So there's more facets to it than just the machine time or the machining that goes into it.
Yeah, and that kind of adds to this layer of complexity, not just part complexity, but complexity in the process. So when we think about analyzing a part for 3D printing, we think of this as a starting point. As if your part is so expensive to 3D print or so unique that it just doesn't register as a valuable production strategy, you don't print it. But if you're going about kind of exploring a metal printing process, whether it be ours or others, it's really important to know a couple things. One, how much is the part going to cost to print on the system you're looking to print? Ours, other systems, anyone, that's really important. And two, like, what is your current production cost curve? And it's easy to kind of look these things out. You can go anywhere as simple as like Proto Labs, which will quote volumes, cost for you at given volumes, or you can look internally. And if you know those two numbers, you can really look to see at what volumes a specific part is reasonable to produce if you're looking to produce it. Now, that being said, there's a million other constraints that determine whether or not you can print a part, whether or not it's physically printable, whether or not it takes too long to print. There's a ton of other things. And so this is by no means saying that if you have a part that fits in the cost curve, you should print 500 of them. That's not at all the way we want you to think. What we want you to think about is this is where it's economically feasible. These are where, if you're looking for opportunities to implement it as 3D printing gets better, as it gets faster, these are the areas you want to look at. And when you're comparing and looking for parts to print, the parts that have that really high, long cost curve are the ones that are going to return you the most benefit if you're looking to do anything in a production sense.
Yeah, that brings up a very good point. There's this idea around 3D printing that it's going to replace all these manufacturing methods that we've been using for the past century. And that's not really true. 3D printing, metal 3D printing included, is another tool that you include in a machine shop or in a factory. And so you're not necessarily you're gonna print every single part on your factory line out of metal. No, sometimes it actually is better to produce parts using traditional methods like die casting or machining. But there are places where you can really optimize, for example, like on this left side of this curve, where you can save a lot of money by leveraging this tool that's being introduced into the industry right now. But if you're going to be making 100,000 parts, and that's well beyond the point where you'll be saving money with 3D printing if we're talking about die cast metal parts.
Yeah, and I think that's really, really important there. It's that 3D printing isn't going to replace casting, machining, forming, any of these tools that have become kind of the main tools that people use. What it will become is a valuable contributor in a space where there's two main axes, volume and complexity. And so in places where you have high complexity and lower volumes, I think that's where you see 3D printing really come in and be more useful. And that's, if you have parts like that, those are the kind of parts you really want to look to print, especially in a metal process. Yeah, that's all I had to talk about explicitly today. But we can answer as many questions as people have.
Yeah, and if there's any part of that you would like us to go deeper in, we're happy to talk about that as well. This is kind of the beginning of a concept that you can explore pretty deeply as we go into talking about how you consider introducing metal printing into your workflow and how that can save you time and money, and how it can also open up more possibilities for parts that you can make that might be infeasible because of cost or other reasons with traditional methods. So feel free to throw us questions in the chat. Otherwise, I can also go deeper into other parts of this.
Yeah, I think one place, if we don't have any questions to start, what about machining? So we talked a bunch about casting here. Machining is a bit different. How would you kind of equate machining to what we're looking at here on a cost curve, and how you compare it to printing?
Yeah, that's interesting, because also you get to the question of that starts creeping into the ROI space, I think, because in terms of machining mass production, I was traditionally taught, if you're going to machine a part, you would never machine something for mass production. But then you look at a company like Apple that machines the casings for their laptops out of aluminum, and they have, they're using factories with literally thousands of CNCs that are machining on a mass production level. So That's not necessarily true.
Mm-hmm.
And the interesting thing that machining brings up is the skilled labor aspect of it. So even if you're using a CNC mill, you still need the skilled labor to actually carry out the cam for that part, which is something that doesn't exist with 3D printing, which adds, moves this curve upward when you're machining a part.
And I think what you'll see with machining on this curve is a shallower curve that starts lower. To machine one part's a lot cheaper to cast one part, but it's one that levels out at a much higher level than casting or maybe even printing. So machining, I think right now is kind of the main player in this really like low volume, high complexity space. And machining will continue to have a role, especially in this like slightly higher volume space. But you'll see, I think for some parts, you'll see 3D printing start to displace machining in that space, because where machining is currently kind of the flattest curve on this. So if you're looking at low volumes, it's better to machine something than mold it for a large quantity, like a large quantity set of parts. And that may well change as we see 3D printing get more prominent.
Yeah, certainly. And I think this brings up another facet of this conversation, where we talk about the overhead price or the overhead cost of tooling with all this mass production, and that's where you see like 3D printing come into the conversation in a different way. So we've really been talking about metal 3D printing in terms of end-use parts, but also you can use 3D printing along with these traditional methods such as casting to drive these curves downward. So for example, if you're doing on the plastic side, if you're making injection molds, yes, you can 3D print injection molds out of metal and finish it on a mill, and then that might cost less than outsourcing it to get tooling done for injection molding. So then you're already driving. So let's say you're injection molding plastic parts. Instead of having tooling cost upwards of $20,000 or $30,000, you can start the curve down by an order of magnitude sometimes, and then drive your cost down that way. So not necessarily making 3D printing your end use parts, but 3D printing tooling to help drive that cost curve downward.
Yeah, and someone just asked thoughts on HP Metal Jet for high volume manufacturing. I would recommend you check out our Gladcast we did last week. We talked a bunch about binder jetting. Their metal jet technology is really just binder jetting. They have for reference, they have a big tub of binder that has basically layer spreading technology, a big tub of powder that they can spread layers on very finely. And then they have a binding system that can come down, that kind of is like a printer inkjet system that lays down binder very specifically to make parts. Its advantage in speed is that you can really do layers much faster than you would with a laser, which is kind of the conventional metal printing powder method. In terms of it for high volume manufacturing, I think we were on the record last week saying binder jetting may well be the future of that kind of high volume complex part manufacturing. The reason we've talked about 3D printing really broadly here in the metal context is because the metal 3D printing as a space is very broad right now. There's I can think off the top of my head about 6 or 8 technologies, a lot of which have been kind of conceptualized or brought to life via a product in the last year or two that are kind of hailing themselves as the future. And so each of those technologies probably has a different curve on this space that fits differently. Something like the Metal X, where the volume is smaller, probably isn't as fit for a larger volume as something like HP's powder bed system. Now that being said, HP has a bunch of questions to answer because like as them or any other binder jetting system happens with the binder jetting process, it's a 2-step process. It's kind of like the Metal X in that it's not you print a metal part and it's there. You print it, you then sinter it, and then you have basically a part that you might need to heat treat or do something otherwise to, or maybe batch machine if you need it precision done. So I believe binder jetting to be super promising. I also believe there to be a lot of questions to happen in fabrication to see how accurate parts can be, how reliable they can be, and how well they translate into that mass production space. But it's certainly promising, and you could see someone like HP being a lot more realistic and pushing their volume out to 10, 20, 30,000 than a part like the Metal X, which is a printer like the Metal X, which is definitely as a filament extrusion printer more limited in its speed capabilities to produce parts.
Yeah. And it looks like we have a question on a cost curve that includes upfront costs. And as I mentioned a couple minutes earlier, this starts bringing up the question of ROI, or return on investment, and how fast you can overcome that initial investment for a 3D printer or other machinery to pay itself off over time. And so this is something I think we're going to explore in further weeks through these AM Fridays. But it's an interesting question because 3D printers, although are an initial step investment that you have to make, metal 3D printing is becoming a lot less expensive. Our Metal X system is looking, 5 or more times less expensive than those traditional powder-based methods.
Yeah.
And so now you're looking at, I can buy a metal 3D printing system that's on the order of magnitude cost of just a couple tools for a die caster. Or something similar.
And I think, and in terms of like what you're looking at from an ROI thing, I think, as Nick said, we'll probably get into ROI a lot more than like a future edition of this. What you look at is you probably look at a chart that has 3D printing where you have kind of it starts higher, but it's a much flatter cost per part, or you apply that cost per part savings against your existing machinery, which costs more. So when you're thinking about ROI or a cost curve that improves upfront costs, what you're looking at generally is how many parts you have to print for a printer to pay itself off, or for a machine to pay itself off. And so that really depends on a couple things. One is the amount you're saving on a per part manufacturing basis, which is directly related to how much your part cost before. And 2 is how much your original investment costs. And so for the Metal X, it's in it's south of 200,000. It's probably in about $170,000 range. And so what you're looking at is how many parts do I have to print? How long would that take to pay off a machine that costs that much money?
Yeah, and it's an interesting idea how a lot of companies looking into going into metal 3D printing is this cost is something you have to overcome and study that ROI to make sure it's a good investment. When in reality, these machines cost less than traditional manufacturing machines. They just don't exist in machine shops yet. Yeah, in most machine shops. And so it's this introduction of a new technology, whereas I see in the next few years, machine shops are going to have a metal printer in them, and it's going to be it's going to be a part of just like the everyday fabrication process.
Yeah. So Brian just noted that that our YouTube link to the original webinar is dead. We had some, in case you weren't here earlier, we had some slight technical issues when we first tried to broadcast, so we had to come up with a fresh stream. So that's why it was a little bit of a hijink at the beginning. Sorry for that. We'll make sure to get it worked out in the future. But thanks for sticking with us. In terms of a note on the ROI, I think that you bring up a really interesting point, which is that when you're talking about looking for an ROI on a mill or a lathe or a stamping machine or anything that's very well established, the path for determining what your ROI is very clear, because the technology is so established. You know exactly how much your parts costs are going to be. You know exactly how much the throughput is going to be, and you know exactly how much your differences are from your steady state to what it is if you buy something new. And that's not necessarily true with printing. So one of the big things that's going to happen in the next few years is you'll see a lot more pedagogy, a lot more established costs and savings and documentation around how 3D printing saves money. And I think you'll see the ROI case for printing become a lot easier to make, because there's a lot more established standards about it.
Yeah. And it looks like Sarah has another good question. How does the reliability of 3D printed parts compare to traditional methods? So this is a question that we could talk about for hours, because it depends on a lot of different things. So it depends on what traditional method you're talking about, what metal 3D printing process you're talking about specifically. But in general, a lot of metal fabrication is like a net approximate shape.
Yeah.
So
near net shape.
Near net shape. Sorry. And so yeah, words.
Fridays, am I right?
Yeah. So near net shape. So even if you're casting a part, for example, a lot of times it gets post-machined afterward to get the tolerances that you want, if you're looking for tighter tolerances. And so we see a lot of similar stuff on our Metal X system, for example. You might be printing an end-use part, but certain geometries have to reach a certain specification, and so you throw it on the mill to get that facing operation or whatever final operation you need. Mm-hmm. And so it really depends on what sort of precision you're looking for in your parts. Because like a lot of metal fabrication processes, it's a near net shape process.
Yeah. So you look at machining is probably one of the few true processes when you're talking about the part you're going to get as close to, like a 5-axis mill is going to yield a part that's as close to your CADed part as physically possible. The reality of the situation on most other methods, casting being a great example, is that you CAD a part and then you make it, and the part's going to be erring by some amount, maybe significant amount in various areas. But all it's really about is controlling the error in the specific areas. A great example for anyone that can go check now is if you go open the hood of your car, you'll see like the engine block is a cast and machine part. So there's areas of the engine block that look really that look rough, that look unmachined, that look not precise, and that's because the precision required is really low. And then you'll look at the actual faces in which something interacts with an engine block, and those are very precise because they've been post-machined. 3D printing, it's a little unclear exactly how it's going to work out. It might be super precise, but I think the odds are much higher that what you'll see is, especially for precision operations, you'll see a method that is more reliant on creating that near net shape part that works for two things. One, parts that don't need to be as precise. So if you're looking at a part that's in like the 5 thou range as opposed to the 1 thou range, that's probably what you're going to see there. And then two is something that can easily be post machined if you need a better surface finish, if you need a more precise fit, like a bearing hole, or something that's holding a shaft, or anything radial that's precise in that respect.
Yeah, and there are processes, traditional processes that are very precise. So, for example, die casting is one process that sometimes doesn't require post machining, depending on how much money you're willing to spend on tooling and inserts for that part. You can get, with holes, 1 thou tolerances with holes in a part, and so it brings back the question of how much are you willing to spend on tooling versus perhaps making a part using a different method and then post machining, and that fits into the discussion of how much volume of this part are you making and what tools you have at your disposal to begin with.
Yeah, and someone just bought a Mark II, which is our desktop composite continuous fiber printer, great machine. And they asked what the tolerances can be or what accuracy you can look for. And to answer that question, I go the short answer, which is about plus or minus 5 thou probably, depending on what surface you're looking at. If you're looking on the XY plane, which is parallel to the build plate, that's what you're going to see. If you're looking perpendicular to build plate, it might be a little bit worse or better depending on what feature you're trying to do. And in terms of more of a general answer, when you're looking at tolerance in printing, because it's especially in kind of layer by layer printing, especially in extrusion printing, it's kind of a complex question because you're not creating a part isotropically. You're not casting a part like you would see in a, or casting or molding a part where the part is created all as one. You're created it in steps. So different features see different accuracies, and different orientations do different yield different accuracies. There's a ton of variables that come into an accuracy in 3D printing, and even something as simple as surface roughness or something like that. But it really depends on the material, depends on the orientation, depends on a lot of stuff. But on our Mark II printers, they're pretty accurate to about 5 thou. I'm pretty confident saying that.
And in reality, that's true across most manufacturing methods. If you're looking at injection molding plastics, that also is dependent on a ton of different variables. Yeah. How long are you willing to let how long are you willing to have a hold time or a cool time for that part to decrease warping? Mm-hmm. And so it brings up the discussion of what sort of leniencies do you have in your process in terms of your design, and how much time you're willing to spend making a part will really inform what sort of tolerance you can get with the parts that you're producing.
Yeah, absolutely. Yeah, and it really depends. And something with the Mark II, if you're looking into that a little bit more, a plastic machine is really interesting with tolerances because when you're printing plastic parts, they obviously have give and play. So even though the parts that we have are the parts that we print are fiber reinforced on the composite side, the actual surface of them is plastic. And so that plastic can give or expand or contract or basically move slightly to account for a harder thing that's next to it. So I've had experiences with bearing presses that work really well on those type of printed parts, even though they're super strong parts, because you're pressing it into a slightly plastic region. And so if you're looking for something that's off by like say 2 thou, that's not as big a deal on plastic as it is on metal.
That's a good point.
Yeah, I think there's no other questions on the YouTube live stream. If anyone else has a question, feel free to ask, and we'll see if we can get to it right now. Otherwise, I think we'll wrap this up and hopefully get back to you next Friday with some more stuff. Yep. Yeah. But yeah, thank you so much for your time today, and we really appreciate you guys tuning in. And sorry for the technical glitch. We'll hopefully get that worked out for future occasions. But yeah, have a great day.
Yeah, thanks for tuning in.